Hello, geometry class. Here we are to discuss indirect proofs, which is lesson 48 in your geometry textbook. Now, in class, we've talked a little bit before about how to change a statement so that you're actually saying the contradiction, or you're saying the opposite of what something is true. So, for example, if I wanted to say something about a counterexample, well, a counterexample is an example that can help prove a statement is false. So you can only use that when you're trying to prove that something is false. When we talk about an indirect proof, it's a proof in which the statement, we're going to first say that what we're trying to prove is false, and then prove that that cannot be possibly true. And so we'll move on with saying since the contradiction cannot be true, then the contradiction has to be false, and therefore what we're trying to prove is true. So there are going to be three distinct steps. The first step in any indirect proof, remember that's what we're trying to do, is an indirect proof. The first step is going to be assume that the conclusion is false. What this means is that you're going to look at what you're trying to prove. If you're trying to prove that x is equal to b, for some reason that's going to be what your proof is, you're going to assume that x is not equal to b. And then you're going to move on after that. But whatever you're trying to prove, the first step in an indirect proof is to assume that whatever you're trying to prove is not true, is false. The second step is to show that this assumption right here is contradicted. I can't even spell tonight. Contradicted by a theorem, or a postulate, or a definition, or some other given information. We're going to again, we're going to back up and we're going to say that whatever it is that we assumed here is going to be contradicted by some other piece of information that we have. The third step is that you're going to say that the assumption must be false. And if the assumption is false, the conclusion, or what you're trying to prove, has got to be true. Those are the three steps. They are listed for you again in your book on page 315 for lesson 48. But these are the three steps that we're going to follow as we practice doing our own indirect proofs. So for example, the very first thing that we're going to practice with is we're going to prove theorem 4-1. And for us, theorem 4-1 is if two lines intersect, they intersect at exactly 1 point. So we're going to prove that they intersect at exactly 1 point. Our assumption is going to be that they intersect at more than 1 point, because if they intersect at all, they have to be at least 1 point. But since we're trying to prove that two lines that intersect, that if they intersect, they intersect at exactly 1 point, our first step in our proof is going to be the assumption assume that these two lines intersect at more than 1 point. We'll call them AB and XY. That lines AB and XY, let's see, intersect at more than one point. Okay, if they intersect at points, let's say we'll call this Q, and we'll say that they intersect at another point R. Okay. So now if these lines intersect at Q and R, we need to show that that contradicts another theorem or postulate. And assuming that X, Y, and AB intersect at both Q and R, that actually contradicts postulate 5, which says that through any 2 points, there exists exactly one line. So if I have points Q and R, those are 2 points that can only go through one line. So if X, Y is not exactly the same as AB, then it can't go through exactly this, it can't go through 2 different points. So now I can say this contradicts theorem 5, which says through any 2 points there exists exactly one line. Since AB and XY cannot both go through R and Q, because theorem 5 is contradicted, then our assumption must be false. False. And 2 lines, 2 intersecting lines can meet or can intersect or can cross at exactly one point. And that is all there is to the proof. Now, you probably shouldn't use as many abbreviations and things like that as I use in here. And you definitely want to make sure that if you say something about theorem 5, that you say exactly what theorem 5 is. But that's all there is to this indirect proof. And the first thing that you're always doing is you're writing an assumption that is the opposite of what you're trying to prove. Let's try another example. Let's look at example 2 in your book. It says, use the diagram to prove theorem 47-2. If an inscribed angle intercepts a semicircle, then it is a right angle. So we've already talked about this in class, and we've done a proof on it already. But let's pretend that we're trying to find another proof. Well, we'll find another proof. And we'll talk about circle M. And we have inscribed angle ABC. Remember, an inscribed angle has its vertex on the circle and its endpoints are also on the circle. And we've got another point on the line out there. So we have a given that AC is a diameter of circle M. And our proof, what we're trying to prove, is going to be that angle ABC is equal to 90 degrees. That's what we want to prove. So we're going to start by assuming that the measure of angle ABC is not equal to 90 degrees. Now, if ABC is not equal to 90 degrees, then ADC, that arc, is not equal to 180. ADC, right? Because remember, ADC is the intercepted arc. And by theorem 47-1, we know that if this is a semicircle, that this arc has to be 180 degrees. And Theorem 47-1 says that any angle, any inscribed angle, is going to be double the angle, or this inscribed angle is going to be 1/2 of the arc that it intercepts. So because we know that this is 90 degrees, then we know that arc AC, the measure of arc AC, cannot be 180 degrees, because 47-1 says that if this is 90, then this has to be 180. And if this is 180, then this has to be 90, right? Because that arc has to be double what the angle is. So if this is not 90, then this cannot be 180. So since this is not 180, and then we know that AC is not a diameter. This contradicts our given info. So our assumption must be false. And the measure of angle ABC must be 90 degrees. Okay. That's really all you need for this particular indirect proof. There's another example in your book that you are more than willing to read through. We can talk about it in class, but I'd like to make sure that you do your lesson practice for this lesson and also the assignment that was given in class. Okay. Enjoy your homework. See you in class. Good night.